So what we did last time around is we took our first step with monads. And what we actually did is we essentially rediscovered the basic idea of what a monad is, although we haven't seen the details of that yet. So what we're going to be doing today is, as usual, doing a quick review of what we did last time around, and then we're going to be giving the formal definition in Haskell for what a monad actually is, and then we'll move on to consider two more examples. So just to begin with our recap of last time around, here is the definition of the bind operator for the maybe type. And what the bind operator is doing here, which is this funny infix symbol here, is it's capturing a form of sequencing for computations that may fail. And you can see that in its type. What we're doing first of all in the first parameter is taking a value of type maybe A. So that's something that could succeed or fail. And then in the second parameter, we're taking a function that tells us what to do with the result value of type A if the first argument actually succeeds. So what we do is we pass that result value into this function. And then finally, in the end, we're going to get back a result of type maybe B. So this is the bind or into or then operator. And again, it captures a form of sequencing for computations that can fail. And the definition is entirely straightforward. I mean, the type is perhaps a little bit weird, but the definition is very straightforward. So we're matching on the first parameter. If the first parameter has failed, and then we're trying to feed that into a function which tells us what to do next, well, we don't have a value for the function, so we're simply going to fail and return the value nothing. So in this case, the then operator, or the sequencing operator, or the bind operator, simply propagates the failure in the first parameter. If the first parameter actually succeeds and we get a successful value x, then all we're going to do is feed that into the function f simply by applying the function to that parameter. So again, just captures a very simple idea of sequencing for computations that may fail. And then what we saw the last day with this is how we could use it to streamline the definition of our evaluation function. So we were writing this evaluation function here, and it takes a simple expression as an input, which can be built up from integer values using a division operator. And the interesting part is that it may fail because we may get a division by zero somewhere. And we capture that here by returning maybe of an integer. So evaluation is a function that could either succeed and return a single integer value, or it may fail and return nothing. So let's have a look at the definition now. So the base case for the definition is entirely straightforward. If you're evaluating an integer value, then there's nothing to do. You just give back the value n, but we must return a maybe value here, so we need to tag it up as just of n. And then the interesting case is, what do we do when we try and evaluate a division? Well, it's kind of a procedure here. We're going to do three things, one after the other. So the first thing we're going to do is evaluate x, and if that fails, then the bind operator will just propagate the failure for us. We don't need to worry about that. But if it succeeds, it will pass the successful integer into the function. So the function here is going to name that, or bind the value of n, and then we'll continue. So then in the second line, what we're going to do is then we're going to evaluate the second parameter y. And again, that could fail, and sequencing will deal with that automatically for us. But if it succeeds, we're going to call the successful integer result value m. So if we get down to the final line now, where we're calling safediv, we have two integers, n and m, and then we can just divide one by the other using safediv. And again, the safediv helper function, it does the division, but if it detects there's going to be a division by zero, it returns nothing, rather than returning or crashing out. So the point here now is that by abstracting out this simple sequencing operator, we've hidden all the plumbing of failure management. There's no actual code in here at all for dealing with the failure management. It's all behind the scenes in the sequencing operator and the safediv operator. So we end up with a kind of very nice operational or imperative style program, which is evaluating an expression. The final thing we saw last day is how you can streamline this program even further by using the do notation, which captures a common pattern of using the bind operator. So if I get rid of this, what we can do now is we can simply write do, and then we can write n comes from the result of evaluating x if it's successful. M comes from the result of evaluating y if it's successful, and if both of those things are successful, then we're simply going to return the result of safe dividing n by m. And again, the point here is that the do notation is just syntactic sugar for repeated use of the bind operator. So when the Haskell system or the Haskell compiler sees all of this stuff here, it simply replaces it by the cascading use of the bind operator and lambda expressions that we just had. But I would much rather write this because it looks more operational. You evaluate x, you evaluate y. If both of these are successful, then you perform the safe division. So this brings us on now to the point where we can actually give a formal definition in Haskell for what a monad actually is. Because as I mentioned at the start of today's class, we've essentially now rediscovered what a monad is. So in Haskell, the class of applicative functors that support a bind operator are simply called monads. So we're going to make a class declaration at this point. So we're defining a class, and we're going to say, provided that you already have a parameterized type that is an applicative functor, I'm going to call it M because it's going to stand for monad now, then you're going to have a monad provided that you have a bind operator, or a sequencing operator if you like. So what we must have is the infix bind operator, and it has exactly the same type as we had for the maybe type, except we're generalizing now, and we take an m of an a, and then if that gives back a result value a, we're going to feed that into a function a to mb, and then finally we're going to get back mb. So this is the general type of the bind operator. So for the maybe type, we wrote maybe A to maybe B, and then we got maybe B. But now we're working with any old parameterized type, which is applicative. So we generalize the type. There's actually one more operator, or one more function, that's part of the definition in order to be a monad. And it's a little function called return. So let me put this in as well. And what return does is it gives you a way of getting into the monad. So it goes from A to M of A. And you might think, well, I've seen something like this before. This is looking like the pure function which we have for applicatives. And actually, it's going to play exactly the same role. And what we'll see is return actually has a default definition, which is just return is defined to be pure. And we have the pure function available to us because in order to be a monad, we must first be applicative. So we know we have the pure function, so we can simply define return equals pure. So this is the kind of 4-line formal definition in Haskell for what a monad is. I mean, the two important points are you need this bind operator and you need the return operator, which is just defaulted to being pure. So before we move on, just a couple of observations to make as usual. So the first point is that the concept of a monad once again comes from category theory. So category theory is a kind of mathematical approach to the study of algebraic structure, and as we've seen already, it gives rise to things such as functors and applicative functors, which have found their way into modern languages like Haskell. The second point I want to make is, what about return? So return is included in the class declaration for two reasons. One is historical reasons, it's always been there, and also for consistency with category theory. If you pick up a category theory textbook and you look to see how it's defined, you will find something with a similar type to return in there. And finally, just to kind of make the comment about return again, it's normally just another name for pure, but if you want to override it, you can. And often when I'm defining monads in this course, rather than simply using the default definition for return, I'll actually manually define return so that we make sure that we all understand what is going on with that. So this is the class declaration. It's again just something that is one of the few things in this course that you just need to remember when you're doing an exam in it. So let's have some examples now. We're going to have 3 examples today. So the first example we're going to look at is, of course, the maybe monad. So let's see how we can define maybe to be an instance of this class. And this is very easy because we've already basically defined this a number of times. So all I need to do is write instance monad and then maybe, and now I simply just need to define the sequencing operator and the return operator. And note that I don't need to make it into a functor and an applicative because we've already done that in previous classes. So what we're going to do then is we write down the type in a comment, as usual. So the type of the bind operator is, we're already very familiar with this. Take a maybe A, and then you go from A to maybe B, and then finally you're going to get back A maybe B. And the definition is exactly as we've seen a few times before now. If you have something that's failed and you're trying to feed it into a function, there's nothing to do. So you simply propagate the failure and get back nothing. And if you have something which succeeds and you get a successful result value x and you want to feed it into the function, you just feed it into the function. And that's the definition. I mean, for this simple example, I'm not actually going to define the return. I'll just use the default definition in the class that says return equals pure. So a couple of points to note about this. This declaration here, so writing instance monad maybe and then defining the bind operator, this is precisely what makes the do notation work for the maybe type. And actually it's what makes the do notation work for any monadic type, because the do notation is a shorthand for repeated use of the bind operator. So if you can define a bind operator and make your parameterized type into an instance of the monad class, then you get the do notation to streamline your programs. So what we're going to see for the rest of today, and actually for the rest of the monad lectures in the course, is more examples of monadic types, and then we'll start to think about what is the benefit of programming in this particular style. So now we're going to have a couple more examples. So the first example I want to show you is how do you make lists into a monadic type. Okay, so we've already made lists into functors and applicative functors, so we don't need to do that again. All we need to do is define the bind operator to make it into a monad. So we can write down the declaration very simply. We're going to write an instance declaration, and we're going to say that the parameterized type for lists, which remember is denoted like this. It's the same as the empty list, but it's not the empty list here. This is the parameterized type for lists without a parameter. And as usual, we write down the type of the bind operator in a comment because that's going to help us to define this operator. So we've got the bind operator, and it goes from list of A, so that's the M of A, and then we go from A to MB, so we go from A to list of B now, and then finally we're going to get back a list of B. So all we've done here is instantiated the type. This is the M of A to MB, and then we've got the MB. So as usual, it's a game with types now, and we just need to figure out how to define the bind operator. So we'll take the parameter, which is the list, x's, and we're feeding it into a function f, and then we think, well, what do we actually do? So as usual, let's think about the types. What is the type of x's and what is the type of f? So x's is simply going to be a list of A. We can just read that off from the definition. That's the first parameter. And then the function is going to go from A to list of B. And again, we can simply read that off from the definition. And then what we want to have on the right-hand side, all of this has got to be a list of B. So we think, how do we do this? So let's think what we've got. So we have a list of A's, and we have a function from A to list of B. So if you have a list of things and you have a function on the elements, a natural thing to do is to map the function across the list. So let's do that. So we could simply write here map f across the list. Okay, and we can think, what is the type of this? Well, if we have a list of type A and we have a function from A to list of B and we map one across the other, then what we're going to get back is all of this is going to have type list of B. Okay, and that's not quite what we want. What we want in the end is we want to have a single list of B. So how do we transform a list of B's into a single list of B's? Well, there's a nice helper function for this in the standard library. We can simply write concat. Okay, and that will give us the right type. So concat takes a list of lists and smashes everything together to give a single list. So this is one possible way to define the bind operator for the list monad. We'll see in a moment what it actually does. Let me show you another way. So let's get rid of these types down here. Let me show you another equivalent way, which some of you may prefer. I could also define it using a list comprehension. I could say we're going to form the list of all values y such that x comes from the list and then y comes from the result of applying f to x. Okay, so let's understand the components of this one. X's is a list, so here we have a simple generator which is pulling one value from a list at a time. So x is going to range over the list. And then what we're going to do for each of those values of x, we're going to apply the function. That will give us a list because that's what the function does. And then we'll take each of those values and then we're going to package them up in a list. So for me, the definition using concat and map is the simplest one, but some of you may prefer the definition using a list comprehension. I mean, they're entirely equivalent. So now we've got our definition. Let me just get rid of this one because I prefer the other one. Let's have a simple example of using the list monad and we'll see what it can actually do for us. So here is an example which I'd like to write. I'd like to write a little function called pairs, and I'm in GHCI here. This is the behavior I would like. I'd like to write a little function called pairs, and what it's going to do is take two lists of things, and it's going to give us back pairs of elements from those two lists. So here I have a list with 1 and 2, and a list with 3 and 4, and what I want back is all possible ways of pairing one element from the first list and one element from the second list. So I'm going to get 4 possible pairs. So I'm going to get 1, 3, that's the two first elements, or I could get 1, 4, or I could get 2, 3, or I could get 2, 4. Okay, so it's just, there's two ways of choosing from the first list. We have a 1 or a 2, two ways of choosing from the second list, so I get 4 ways of choosing a pair, one from each component. Again, this is just like Cartesian product for lists rather than sets. So that's the little function I'd like to define. Let me show you how I could do this using the fact that lists are monadic. So because we have this monad declaration, we can now use the do notation to write programs that process or generate lists. So let's see how to do the pairs function. So I can define pairs, and it takes a list of A's. It's going to be polymorphic, and it takes a list of B's, and it's going to give back a list of pairs of A's and B's. And how do we define it? Well, I'm simply going to say if I have two lists X and Y's, then I'm going to do something. So I'm moving into the list monad now, so I have the list monad syntax. I have the do notation. So what I'm going to do is simply select one possible value from X's. So I have this simple generator here. I'm going to select one possible value from the list Y's. So I have a second generator here, and then I'm simply going to call return of XY. Okay, so the way you think about this is very operationally. You've got two lists, X's and Y's, and all you're going to do is choose one value from the first list in all possible ways, choose one value from the second list in all possible ways, and then we're going to return the pair X, Y. And just a point to note here, when you're programming in monadic style rather than applicative style, you tend to use return rather than pure, even though these are exactly the same thing in most cases. So you're probably looking at this and thinking, well, I've seen something very, very similar to this before. This looks very, very much like the familiar list comprehension syntax in Haskell. And you're quite right. I could have written this using a list comprehension as well. So let me show you how I could have done that. Here's an alternative way of defining the pairs function using a list comprehension. I could have written pairs x's, y's, and I form the list of all pairs x, y, such that x is drawn from x's and y is drawn from y's. So if I had asked you to define the pairs function, this is probably what you would write down. It's a simple list comprehension. You have one generator drawing for x, another generator producing values for y, and then you package the two components up. And what you see above is we've got exactly the same components in the monadic definition. We have a generator for x, a generator for y, and then we're packaging the two components up and we're returning them. And you might say, well, why do I need all this labor of this fancy do notation and monads? Why can't I just define this using list comprehensions? And of course you can. These two definitions are essentially equivalent, but there's a big important benefit of using the do notation, and it's that the do notation is not specific to lists. The list comprehension notation down the bottom here to define pairs, that only works for lists, but the do notation works for any monad. It works for the maybe monad, works for the list monad, it works for any monad that we care to define. So it's using the kind of idea of the list comprehension notation, which is a very simple but powerful way of processing lists, and it's essentially generalizing it to work for a larger class of types. So for our last example today, I'd like to look at what's called the state monad. And as we'll see, this is probably the most important monad which we're going to learn about in the course. And the background to this is that suppose we want to write programs that manipulate some kind of state. And a state is just a value that changes or possibly changes over time. So the first thing we're going to do here is declare a couple of types to help us. So we're going to declare a type for the kind of state which we're manipulating. And for now, it doesn't matter what this actually is, so I'm not actually going to give a concrete definition for this. I'll just write 3 dots here to symbolize that you could have any kind of state that you want. Of course, when you come to do real applications, you'd need to fill in something here which is appropriate to the application area. But for now, we'll just leave it undefined. When you're programming with state, the most basic kind of thing which you will do is consider what's called state transformers. So I'm going to declare a type for this. So a state transformer is simply going to be a function which takes in an input state and then is going to give me back a possibly modified output state. Okay, so again, the way you think about this is like the current version of the state coming in, and then you get back a possibly modified or updated state coming out. So that's the basic idea of what a state transformer, abbreviated capital S, capital T, is. However, it turns out that this basic type is maybe not sufficient for all applications. Sometimes you also wish to return a result value. For example, if your state was a counter, maybe you'd want to increment the counter and then return the previous value of the counter as your result value. So what I'm going to do then is modify the return type. So I'm going to get rid of the state type here. And I'm actually going to return a pair comprising a result value of some type A and then the possibly modified state. So now a state transformer takes the current version of the state, gives you a result value of type A, and it gives you a possibly modified state back. But of course I can't just leave that little A sitting there on its own. I now need to make it into a parameter of the state transformer type. Let me just move that over a bit. And this is the state transformer type that we're going to be working with. And the way you read this is, if you have a state transformer of type A, you take in an input state and you get a result value of type A, and then you get back a possibly modified output state. Okay, so very nice, simple idea. It turns out to also be very useful to draw these things in pictures. And you draw exactly what you'd expect. You can think about a state transformer as being like a little box, and it's a function that takes a state as an input, like S. And what you're going to have on the right hand side is it's going to give back a possibly modified state. So let me call that S prime. And then you're going to get your result value. So let me call that V. Okay, so I've got a state coming in, which I'm depicting as the little s here. I've got a result value of type A coming out, which is the value V here. And I've got a possibly modified state coming out as well. And we'll be drawing pictures to illustrate state transformers, and what we'll see is that the pictures will really help us. So you might think, well, I've generalized the type now so that you can take or you can give back return values, because we have this parameterized type st of a, you get an a in a state. Do I now need to go on and generalize it so you can also take additional inputs or argument values? But in fact, you don't need to do this, as we'll see, because currying already gives us the power to do this. So let me explain this with a simple example. Here I've got a function, or let's imagine we have a function which takes a character as an input and then gives you back a state transformer which is going to return an integer. So this is a state transformer, takes a character and gives you back an integer. However, this type here is just an abbreviation. We know that a state transformer really takes a state as an input and then gives back a pair of a result value and a new state as an output. So what we can do then is expand this out. So if I get rid of this and expand it out, what we'll be doing then is we're taking a state as an input. Oops, pen stopped working. And what we're giving back is an integer and a new state. Okay, so this bit here is just st of int, but expanded out. And what you see now is that this is a curried function, which is taking a character as its input, and then a state as an input, and giving you back a result value and a new state. Okay, so the idea of currying has given us the power to already take this additional input, which is the character. So again, we could draw a picture of this. Let me show you how to do this. So we just have a little box. And this time we're going to have a state coming in, that's S. We're going to have a character coming in, that's C. And we're going to get a result value coming out, which in this case is an integer n. And then we're going to get a possibly modified state coming out as well. So the character C is the input character. Then we have a state coming in, which is a little s. Then we get an integer n coming out, and we get a possibly modified state coming out as well. So what we have now is a parameterized type st. And what we would of course like to do now is to try and make it into an instance of the monad class. But there turns out to be a little technical wrinkle here. In order to make things into instances of classes, they need to be data declarations, whereas at the moment, the st type is a type declaration, which is just an abbreviation. But it's very easy to redefine it as a data declaration. So all I'm going to do is write data, which introduces a new data type, and I'm going to call it st, just like we had before. And then on the right-hand side, I'm going to write exactly the same as what we just had. So you take a state as an input, and you give back a result value of type A, and possibly modified state. And the only change I'm going to need to make here is that when you define or declare things as data types, you need to give them constructors. Just like with our expression data type for the example we've been thinking about, we had the val constructor and we had the div constructor. We need to write a little data constructor in here. So I'm going to keep it as short as possible. So I'm just simply going to call it S for state. Okay, so the only changes here is I'm declaring it as a new data type, and I need to introduce this constructor here, which is kind of like a dummy constructor. We don't really care about it at all. And I'm actually going to make one extra little modification in order to make sure that this dummy constructor S doesn't have any runtime overhead, because it's basically just going to be in there to keep the type checker happy. What I'm going to do is use a nice Haskell feature where you can write new type here. And that's exactly the same as a data declaration, except you can only use it with data types that have a single constructor, and it just makes sure that this constructor doesn't actually have any overhead at runtime, because we're going to be kind of tagging and untagging things with S's all over the place, and we want to make sure that doesn't incur a runtime overhead for us. So we use the new type mechanism for that. So the very last thing I want to do before we move on to making this thing into a monad is we're going to have a way of actually applying one of these things, and that's going to essentially get rid of this little dummy constructor S for us. So I'm going to define a little application function called app, and what it's going to do is it's going to take a state transformer st. So here we have our dummy constructor S, which is here. Here we have our state transformer, which is one of these functions. And then what are we going to do? Well, we're going to take a state as an input, and then we're simply going to apply our state transformer to that input state S. Okay, so all this application function is doing is it's basically getting rid of this dummy constructor here, which we needed to put on just to keep Haskell happy, because you can only make data types or new types into instances of class declarations. So we can think, what's the type of the application operator or the application function? Well, app is going to take a state transformer whose result is of type A. That's the st thing. Then it's going to take a state, that's the S, and it's going to apply one to the other, and you're going to get back the result value of type A and the possibly modified state. Okay, so again, basic idea is very simple here. We're applying a state transformer to a state, and we just apply the underlying function to the state, and we get exactly what we expect. So what we're going to do now is move on to making this data type or new type st into an instance of the monad class. And in order to do that, of course, we first need to make it into into a functor and into an applicative functor. And I'm actually going to leave that as an exercise for you. If you're studying this course in Nottingham, I mean, you can just have a look in the book chapter, which I've made available to you online, and you can see the definitions here. If you're studying this course outside of Nottingham, you can try this for yourself, or the solution to this is actually in the book as well. So the name of the game now is that we need to make the st parameterized type into an instance of the monad class. So we write instance monad st where. And as usual, we're going to use types to help us to write the definitions of the component functions. So let's start with the easy one first. Let's start with return. So I'm not going to use the default definition, return equals pure, because I want us to all understand how this is actually working. So what is the type, first of all, of return? So return simply takes in an arbitrary monad. It goes from A to M of A, but here M is the parameterized type st for state transformers. So return goes from A to st of A. So we can start to write the skeleton of the definition. Return is going to take a value x, and then it's going to build me a state transformer. And a state transformer always begins with the dummy constructor S, and then inside it's going to be a function which takes an input state, so I can build a lambda here, an input state S, and then it's going to return me a result value, we don't know what that is yet, and a possibly modified state, and we don't know what that is either. Okay, so here I've just by thinking about the types, I've written down a basic skeleton for how return is actually going to look. So now let's think about the types in a bit more detail. If I look at the parameter x here, that's coming in, that's the A, so that has type A. And then if I think about the S here, that's going to be a state coming in. So that's going to be a state. And then the other two components here, I'm going to have a result value of type A coming out. And I can read that off again from the return type. We get a state transformer of type A, so we're getting a result value of type A. And then finally, the state coming out here, well, the second component of the pair, is going to be a possibly modified state. So now we've got the components, we now think, how can we fill in the two question marks? And of course, this is very easy in this case. We need an A and a state, and we already have an A and a state. We've got X and S. So the only sensible thing to do in this case, because we don't have any way of transforming A's, and we don't have any way of transforming states, we need an A and a state, we've got them, so we simply return them. So I can take the question marks away now and simply return the value X here and the state S here as well. Okay, so let me just get rid of the types now and just explain again what we've just done. So return of x, simply we have a dummy constructor because we need that. We take in an input state s, we give back the result value x, which we were already given, and we give back the state unchanged. So what's really going on here is that return converts a value into a state transformer that simply returns the value x without modifying the state s. So we can draw a picture of this, which might help to explain what's going on. So what we've just defined is the return function, and what it's going to do is it takes in input value x, which I can draw up here. It takes a state s, which I can draw down here, and then what it's going to do is simply pass these things through completely unchanged, and that's what you see in the definition. See up here, I just use a different color. We're taking in the input x and we're passing it through unchanged, and we're taking in the input s and we're passing that through unchanged as well. Okay, so if I just wanted to illustrate that things don't get changed, let me maybe put some dots here. So these things just inside the box go through without changing them at all. So you see here return is doing something trivial and it's doing essentially nothing at all. It's just passing the state straight through, goes through here, and it's passing the input value straight through as well. So you might think, well, why is this actually useful? But when we come to start writing monadic programs using the state monad, we'll see that the return operator is very useful. So what we need to do now, finally, to complete the declaration of the state monad is to define the bind operator. And remember, in general, bind goes from M of A to MB to MB. So in this case, we're going to go from ST of A to A to ST of B. And finally, we're going to get back an ST of B. So what we'll do then is, as normal, we'll let types guide us. So we'll write down a simple skeleton. So we take a state transformer ST, and we're feeding this into a function f, and we're going to build a state transformer. So we need our little dummy constructor, and we take in the input state s, and then on the right hand side here, what we're going to need to do as before is we're going to need to return a result value, in this case of type B, and we're going to need to return a possibly modified state. And actually this time around I need to make a little bit more space here because the declaration or the definition is a bit longer. So let me rub this out for now. So let's have a look at the component types first of all. So first of all we have ST sitting here, and that's going to be a state transformer of type A. So that's very straightforward to write down. That is an ST of A. And then we have F, and that's a function from A to ST of B. So we can write that one down. It's from A to ST of B. And then we think about what's the state here. Well, that's just a state. And then on the right hand side over here, ultimately we want a pair comprising a result value of type B and the new state, because that's what we need to be producing back at the end. So we've got these components. What could we actually do? Well, the first thing to think is, well, we have a state transformer here and we have a state. And the whole point of a state transformer is that you want to apply it to a state to get a result value back, in this case of type A, and a possibly modified state. So the first thing we could do then is simply apply one to the other. So let's apply the state transformer to this state. And I'm going to use a little let here. So I'm going to say let. So we're going to get a result value, x, and a possibly modified state, s prime. And that's going to be obtained by applying the state transformer st to the input state s. Okay, so what we've got back now is we've got a value x, which is of type A, because it came out of the state transformer, which gives results of type A. And we get back a possibly modified state s, which is a state. So now what do we think? What can we do with what we've got left? So what we've got left now is our function f, which takes in a value of type A and then is a state transformer. And that state transformer is expecting a state, and then it will give me back a value of type B and a new state. And what we want fundamentally on the right hand side here, which we're filling in, is we want back a value of type B and a new state. So what we can see then, we can do is if we take the function f and we simply apply it to the value a, or the value x of type A, that will give me a state transformer, which I can then apply to the new state s prime, and that will give me back exactly what I want. So let me write that down. So let's get rid of all this stuff. So if I simply now, if I apply the function f to the result value x of type A, that will now be a state transformer of type B. I can read that off from up here. That's what happens when you apply f. You get a state transformer of type B. If I now take that state transformer and I apply it to the latest copy of the state, which is s prime, this will give me back a pair comprising a result value of type B and a possibly modified final state. Okay, so again, this is one of these points where it's not really much of a spectator sport, watching someone kind of track through all these definitions and all the types and making sure everything fits together. But this is what you need to learn how to do to write monadic things or monadic instances like this for yourself. So what I suggest you do is kind of pause the video, kind of put it away, try and do this for yourself and make sure you end up with the same definition which we've got here. So what I'd like to do to wrap things up today is just show you a picture of this, and actually the picture I think very clearly explains actually what's going on with this definition above. So what we're doing is we're composing two things. We have a state transformer st and we're feeding its result into a function f, and all that's happening in the code above is we're taking in an initial state s, and then what we're getting out is a possibly modified state s prime and a result value x, and these are going into the function f. That's what we see down here. We're applying the function f to the input or the result value x, the possibly modified state s, and then what we're going to get out on the right hand side here is a possibly modified state s double prime, say, and a new result value, let me call that x prime. I mean, these are not named above because when we apply the function or the state transformer f of x to s prime, we just get back the pair. But just to make it clear here, I've called this final state s double prime and the final result value x prime as well. So that about wraps things up for today. We've finally managed to complete the definition of the state monad. And as I think you've seen, it's a bit of a more sophisticated example than the maybe monad or the list monad. But what we'll see next time around is the payoff for this extra sophistication. We'll see how you can use it to write very clean and concise programs which manipulate state in a pure language such as Haskell. So that's it for today. I will see you again next time.